All right, so we're gonna go ahead and start. This one's really short, so it shouldn't take us very long. I'm not gonna read over the charts that are in here because I don't know that that's gonna help anyone. Yeah. We'll wait just a second. I'll go ahead and write some stuff on the board while we're waiting on some people. All right, everybody good? All right, so we're going to start at page 391. All right, so the first word that we see is nutrition. This is a term that refers to the food that we eat and the nutrients they contain. So that's pretty simple enough. Metabolism is how the body uses nutrients after they've been digested, absorbed, and transported to cells. So after we have eaten something, after it's been squashed up and mixed around, after things have been absorbed into the blood and lymph, now what happens to it? Metabolism is what's going to be happening after all this process. So nutrients may either be used as a source of energy or building blocks for making complex chemical compounds. All right, so before they can be used by cells, nutrients have to be assimilated. And this means when nutrient molecules enter cells and undergo various chemical changes. Chemical reactions that release energy from nutrient molecules are called catabolic reaction. Catabolism is vital because it is the only means by which the body can supply itself with energy to do work. So catabolism releases energy as it breaks down nutrient molecules into smaller molecules. So the smaller it gets, the more powerful it is. On the other hand, anabolism is the process that builds nutrient molecules and combines smaller molecules to more complex chemical compounds. These work together, so catabolism plus anabolism is metabolism. Definitely, I would know those bolded words. All right, so liver secretes bile. We've already went over this, but she's wanting to know what all of the functions of the liver are. She's definitely going to want to know those because she told us that during review. So liver secretes bile. Bile or physically or mechanically breaks down large lipid globules into smaller droplets of liquid that are more easily chemically broken down. So bile is going to break down lipid globules. Liver maintains normal blood glucose levels for several hours during following a meal by storing glucose when blood levels are abundant and then releasing glucose when blood levels drop. Trying to highlight my stuff. All right. Liver cells carry on the first steps of protein and lipid metabolism and synthesize several kinds of protein compounds. When released into the blood, they're called blood proteins or plasma proteins. Prothrombin and fibrinogen are two of the plasma proteins formed by liver cells and aid in clotting. So prothrombin and fibrinogen, those two are questions in here. And we talked about these before when we talked about the blood chapter and cells, I believe, that you have to have prothrombin and fibrinogen. These are plasma proteins, and these are what's going to rush to the site to close up a wound, and fibrinogen is going to kind of like fibers that overlap to help with that. So liver cells carry on the first step of protein that synthesize these many protein compounds. Liver cells make a protein called albumin, and this helps maintain normal blood volume. So volume, I think about putting like ice water in a glass, ice and water. When the ice melts, it's not going to make the cup overflow. It's going to be the same level that it was before. You want to maintain a certain volume like that in your blood. So liver can detoxify toxic substances such as bacterial products and certain drugs. We already know that it detoxifies, so the liver is going to kind of process out some stuff before it gets into the body. It's kind of protecting us. The liver can store several useful substances, notably iron and vitamins A and D. So the liver stores iron, vitamin A, and vitamin D. Hepatic portal veins deliver blood directly from the GI tract to the liver and allows the liver to process it before sending it back out. So then we look at macro and micronutrients. Macro is going to be our carbs, lipids, and proteins, and micro are going to be vitamins and minerals. The next thing that I have is table 17-1. If you got the study guide, I had it where you could like fill in some of the stuff. I'm not really going to go over those. We know that mono is 1, di is 2, poly is many. Triglyceride is 3. And then we have our cholesterol, we have protein. All right, carbohydrate metabolism. This has been my least favorite part of the entire chapter, but here we go. Carbohydrates are the preferred energy nutrient of the body, and glucose is preferred energy for most of the body cells. We all love carbs. We all love sugar. Carbohydrates are the preferred energy nutrient of the body. So eat a lot of carbs. It can be a good thing. It can be a bad thing. Glucose or sugar is the preferred source of energy for most body cells. So our cells want glucose. Our body wants carbs. Our body wants potatoes. They want carbs. And our body cells want sugar. Guess like we can memorize that because sometimes like if you put a stick on a cell, it would look like a sucker, and that's sugar. That's glucose. So our cells want glucose. Our body wants carbohydrates. Glucose catabolism is a breakdown. Involves 3 series of chemical reactions or metabolic pathways. So we have glycolysis, the citric acid or Krebs cycle, and electron transport system. So storage, glucose is stored in glycogen in the liver and muscle cells until needed to make ATP. It's just holding on to it until we need that energy. Anabolic glycolysis, glycogen breaks down into molecules and is released into the bloodstream. In cytoplasm, each glucose molecule undergoes glycolysis, which splits a 6-carbon glucose molecule into pyruvic acid molecules, producing a net of 2 ATP molecules. I don't have a way to memorize those other than just keep writing it over and over. But I think she's probably just going to want to know the pathway, like the steps. Fate of pyruvic acid. Each pyruvic acid is converted into 2 acetyl molecule, which is escorted by coenzyme A into the mitochondria, where it enters the citric acid cycle. This releases 1 molecule of carbon dioxide. Then we have the citric acid cycle. Each acetyl CoA breaks into 2 carbon dioxide and release many high energy electrons. Then we have the electron transport system. The electrons are transported along the inner mitochondrial membrane and release their energy, which generates 30 ATP molecules in the presence of oxygen. And ATP is energy. Adenosine triphosphate, or ATP, is the direct source of energy for doing cellular work, so we have to have this. It's the most important biological compound, energy, because if we don't have it, we're not living. Energy within ATP is released most instantaneously and can be directly used to do cellular work. So release of energy from nutrient molecules occurs in a lot slower because it's transferred to ATP molecules first and then will be explosively released from them. ATP is made up of adenosine phosphate group and 3 phosphate groups. Its capacity of large amounts of energy is found in its bonds, and when a phosphate group breaks away, it results in ADP molecule and a free phosphate group. Energy bond is then free to do cellular work. I'm going to draw a picture of this in just a second. Energy produced by the carbohydrate catabolism reunite with the ADP and phosphate group. This loop continues as ATP is made to meet cellular demands. Only enough ATP for immediate cellular requirements is made at one time. Glucose that is not needed immediately for ATP production is built up by anabolic processes into larger molecules that are stored for later use. So this, they had a picture of. I drew a picture of it as well. Okay, so we have, this is going to be ATP. All right, so we have one adenosine molecule. You guys see that? Okay. All right, and then it's connected with 3 phosphate groups. It's not bad. It's not going to be bad. All right. So I have adenosine and 3 phosphate groups, and these are connected with high energy bonds. My little squiggly lines are going to be the high energy bonds. So these are relevant, but these squiggly lines, the bonds are where the power is coming from. This is the most important part. So this is energy. And we're going to do this. We have adenosine, and now we have 2 phosphate groups. All right, so 1 phosphate has broken away. This is ADP now. So this is ATP and this is ADP. It's lost 1 phosphate group. This okay, I'm gonna try and break it down a little bit better. Okay, let me try this again. It makes sense when I'm writing it out, but it's hard to explain it. All right, so this is ATP. This is energy. ATP essentially is energy. So we have an adenosine. This is all this is an adenosine molecule. And then we have 3 phosphate groups. Okay, so this is just the building blocks for energy. 1 adenosine, 3 phosphates, and then you have these high energy bonds. I was going to say electricity. All right, so high energy bonds. High energy bonds. These are the most important part. Most important. All right. So then the next part I have is just put this in the back part of your brain for just a second. This is a whole piece of energy, if you will. All right, we have our adenosine again. We have 1 phosphate. Here's our strong bond. Here's our other phosphate. Here's our strong bond. We lost a phosphate. We moved our arm. We contracted our arm, and we used the energy. So 1 of those phosphate groups went away. This part right here is the energy working. These are just the building blocks. This part right here is where the contraction happened. So this is ADP now. It can't be ATP. It doesn't have all these parts. So now this is just ADP. All right. So this high energy bond is where the energy comes from to be used, for example, in a muscle contraction. So this is energy. And then this is energy being used. So basically, let's say that this is an outlet in the wall. It's just holding energy. And then this would be a waffle maker. We're gonna use that for energy. This is just holding energy, and this is using energy. All right, so ADP can be made into ATP again. The ADP and phosphate reunite to make ATP again, and then energy is being replaced. So the cycle keeps continuing. So we have energy, adenosine, 3 phosphates. Now I need to move a part of my body. So to use this, I'm going to get rid of one of those phosphate groups, and this is going to be the electricity being used. So now this is ADP. It can't be ATP anymore, it's ADP. Adenosine diphosphate. Di would be 2. Adenosine triphosphate, that's 3 phosphates. Adenosine diphosphate, di meaning 2 phosphates. Does that make sense? All right. So then when we want, when we need more energy, a phosphate group is going to be added, and then it's going to be ATP again. So it's just a cycle that comes back around, comes back around, comes back around. We got to keep having that energy. Okay. No, you're fine. You're fine. All right. I can run through it one more time if you want me to. All right. So we start out with ATP. We're going to use that energy, and we're going to have ADP, and then it's going to go right back to ATP when the phosphate group joins. But the main part of is just knowing how to break down a word. So D and T, triphosphate 3. 3 is tri, 2 is di. So then we know how many phosphates we needed. Adenosine, tri, 1, 2, 3, phosphates, 1, 2, 3. All right. All right, so calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. A kilocalorie is something written as calorie with the uppercase C, a larger unit. There's 1,000 calories in 1 kilocalorie. I think she just wanted us to know what a calorie was. It's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. All right. Glucose anabolism. So we know glucose is sugar. And anabolism is building something up. All right, so glucose anabolism is called glycogenesis. All right, this is carried on in the liver and muscle cells and consists of a series of reactions that join glucose molecules together to form glycogen or an animal starch. So when I think Genesis, I think like the first book in the Bible, like everything's kind of being born, but like everything's kind of being built up. So sugar being built up. All right, so glycogenolysis, when glucose stored as glycogen is needed to make ATP, breaks down glycogen chains in the liver or muscle cells to release individual glucose molecules. This is an example of catabolism. Catabolism is breaking down. Regulation of carbohydrate metabolism. The amount of glucose and other nutrients in the body normally doesn't change very much, even when we go a few hours without food, when we exercise and use a lot of nutrients for energy, or when we sleep and use a few nutrients for energy. It's going to kind of stay relatively the same. Glucose in our blood normally stays about 80 to 110 milligrams in 100 milliliters of blood when we're fasting between meals. She did say to know that. We need to know what the regular for that is. Insulin is known to accelerate glucose transport through cell membranes. And insulin secretion increases, more glucose leaves the blood and enters the cells, particularly liver cells. Too little insulin secretion or resistance to insulin effects in people with diabetes mellitus produce the opposite effect. Less glucose leaves the blood and enters the cells. More glucose then remains in the blood and less glucose is metabolized by cells. In other words, high blood glucose or hyperglycemia and a low rate of glucose metabolism characterize insulin deficiency. And insulin is too lower blood sugar. All right, this is where I was talking about she did say to highlight this, that we didn't need to know it. Insulin is the only hormone that significantly lowers blood glucose level, but there are many that raise it. Glucagon, cortisone, growth hormone, and epinephrine will raise blood sugar. Lipid metabolism is next. Oh, sorry, we had a health and well-being block. I don't know if she's going to want to know this, but you never know. Loading up on carbs basically is carbohydrate loading or glycogen loading. This is a strategy that is sometimes used in athletes to max their ability to store glucose. So they usually switch to a high carb diet 2 to 3 days before an endurance event. So just like we had where they would get a blood transfusion and have a lot of oxygen, they kind of do the same thing but with sugar. They're going to eat a lot of carbs 2 to 3 days before. Oh, all right, so we have lipid metabolism. Lipids are primarily energy nutrients. Fats are energy nutrients. As glucose supplies drop a few hours after a meal, cells immediately begin to catabolize lipids for energy. So as soon as we get finished eating, our cells are going to start breaking down fat for energy. Lipids are broken down into fatty acids and glycerol. Remember, we said that the end result of lipids are fatty acids and glycerol. And then each of these is converted to a chemical form that can enter the citric acid cycle. When a person goes without carbs for a few hours, abnormally in individuals with untreated diabetes mellitus, so because too little glucose enters the cells break down lipids instead. In all people, lipids not needed for catabolism are anabolized to form triglycerides and are stored in adipose tissue. And adipose tissues are fatty tissue that we talked about. That's just the extra spare tire on us. So when they're not needed to be broken down for energy, these are going to be stored in our fat. Protein metabolism. In a healthy person, proteins are catabolized to release energy in a very small extent. When fat reserves are low, like in starvation or anorexia nervosa, the body will rely more heavily on its protein molecules as an energy source. Gluconeogenesis, amino acids that make up proteins are each broken apart to yield an amine group that is converted to form of glucose that can enter the citric acid cycle. So basically, it's just trying to break everything apart and move it where it needs to go so that this body can get energy. That's the whole purpose of this. Keep going over that cord. Let's see. Gluconeogenesis is performed in liver cells. That's another function of the liver. All right, so a more common situation is protein anabolism. This is building up, where the body builds amino acids into complex protein compounds. Proteins are assembled from a pool of 20 different kinds of amino acids. If any one type of amino acid is deficient, vital proteins cannot be synthesized, which is a serious health threat. One way your body maintains a constant supply of amino acids is by making them from other compounds already present in the body. So only about half of the required 20 types of amino acids can be made in the body. The rest of them have to be supplied in the diet. So you have essential and non-essential amino acids. Essential have to be in your diet. Non-essential can be missing from the diet because they can be made in the body, so we're not missing them. We have micronutrients, which are your vitamins and minerals. I already took that off the board, but vitamins, carbs, lipids, and proteins are used by our bodies to build important molecules and provide energy. Vitamins are organic molecules needed in small quantities for normal metabolism. You can buy these at the store. Most vitamin molecules attach to enzymes or coenzymes to help them work properly. And minerals do the same thing. Minerals attach to enzymes to help them work properly. So they're just aiding in something. Many enzymes are totally useless without the appropriate vitamins to activate them. And that's kind of scary because I don't know if I've been getting any of those in my diet, and I'm sure I'm not taking them. Most vitamins cannot be made by the body, so we have to have them in our diet. This is one she definitely said we needed to know, that lipid-soluble vitamins are A, D, E, and K, and they're stored in the liver for later use. And the way that we memorized this before was ADEK, A-D-E-K, are lipid-soluble vitamins. These are stored in the liver. ADEK are stored in the liver. ADEK are stored in the liver. Water-soluble vitamins B and C are continually peed out. B and C we have to take. We have to take B and C because we pee them out every day. Vitamin deficiencies can lead to serve metabolic problems, so we have to have those if we want to have correct metabolism. Minerals are just as important as vitamins. They're inorganic elements or salts that are naturally in the earth. They can attach to enzymes to help them work. Again, they do pretty much the same thing that vitamins do. They're just a little bit different. Sodium, calcium, and other minerals are required for nerve conduction and for the contraction of muscle fibers. So if we don't have those, things start shutting down. All right, we got just a little bit more. I'm going to skip tables 17.3 and 17.4. I can't know those for you. So regulating food intake. I have a feeling she's going to ask us about this because she seems to like the brain or the nervous system. So hypothalamus plays a part in mechanisms for regulating food intake. We have an appetite center that tells us when we're hungry, and then we have a satiety center, which promotes a feeling of fullness or satisfaction. The balance of activity between these two centers appears to be the central mechanism that regulates food intake. Many factors identified affecting appetite are hormones, neurotransmitters, emotions, environmental cues, food sensations, habits, and more. So all of these can affect our appetite. All right, so we have a metabolic rate. Basal metabolic rate is the rate at which nutrients are catabolized under basal conditions, awake but resting. So when we're chilling out, that's our basal metabolic rate. It's the number of calories of heat that must be produced per hour by catabolism or breaking down, just to keep the body alive, awake, and comfortably warm. To provide energy for muscular work and digestion and absorption of food, additional nutrients must be catabolized. The more active a person is, the more nutrients the body must catabolize, and the higher the total metabolic rate will be. Total metabolic rate is the total amount of energy used per day. So at the end of the day, the total of energy that you used is the total metabolic rate. When a number of calories in your food intake equals your total metabolic rate, your weight will remain constant except for possible variations resulting from water retention and water loss. When your food intake provides more calories than your total metabolic rate, you gain weight. And then when your food intake provides fewer calories, you lose weight. So reducing diets make use of this knowledge. They contain fewer calories than the TMR of the individual eating the diet. Your body temperature, it says considering that 60% of energy released from nutrient metabolism is converted to heat rather than being transferred to ATP. That's probably going to be something that she'll ask. All right, so maintaining constant body temperature is a challenge, and the homeostasis of temperature is thermoregulation. It's the function of the hypothalamus. Again, the hypothalamus is controlling something else. Let's see. It operates in a negative feedback mechanism that keeps body temperature in a normal range. We keep seeing negative feedback too. Normal body temperature range is going to be 97 to 100. She did say to know these. Skin's often involved in negative feedback loops and maintain body temperature. And when the body's overheated, blood flow to the skin increases because we're trying to get that heat out. We're trying to sweat it out. We're trying to move it out. And there's 4 different ways to do that. There's radiation, conduction, convection, and evaporation. So radiation is the flow of heat waves from the blood and skin. I put like heat leaving your head. I'm trying to remember those pictures in the book. Conduction is the transfer of heat energy to the skin and then to cooler external environments. So it's coming to our skin and then it's leaving. Heat leaving your body into an ice pack. Kind of think of like the ice pack pulling it out. Convection is the transfer of heat energy to cooler air, eventually flowing away from the skin. And I put like a fan blowing away your heat. Evaporation is the escape of heat from the blood and skin by water or sweating. Heat can be conserved by reducing blood flow to the skin, and it can also be conserved by reducing any of the 4 mechanisms that we just said. Heat generating muscle activities such as shivering short-term and secretion of metabolism regulating hormones long-term are 2 of the body's processes that can be altered to adjust the body's temperature. All right, does anybody have any questions? That's the end of that. All right. If we don't have any questions, I'm going to go ahead and get off here and start working on these tables we have to memorize.